Okay. All right. Welcome. Okay, we're on the second exam. Just kind of polling people. How confident do you feel? How many people are ready for this exam? Yeah. It's good. Bring it on. And how are you doing in chapters 7 and 8? That's kind of the last stuff. I think when you catch on to things from 7 and 8, they're pretty simple methods, and so hopefully you're kind of catching on to that, and I'll do some more examples today, but there'll be on the exam, there's kind of these two parts. There's a Newtonian perspective as well as the energy perspective. Yeah.
Is there going to be like integration associated with energy problems on the exam?
It's certainly possible. Generally, we're going to be dealing with like conservative forces, and in a sense the one we would do an integration, and I'll do it, is like the potential energy of a spring. I don't think there's going to be a lot of questions where that might come up, but maybe hang on to that question as we get into it. We'll look at something like that. So, okay, so we start off with this chapter 5 and 6. Is really, we say, the Newtonian methods and Newton's laws of motion. They say there's 3 of them. The first one is kind of the general one that objects in motion tend to stay in motion, and objects at rest tend to stay at rest. If they are in motion, they tend to travel in a straight line. They'll just go right on across the universe unless acted on by a force. And we mostly pick up on the second law, where we say that this is old F equals ma, and it's probably best to think of this as it's really the sum of all the forces. It's really that is the net force, and it's probably easiest to think of this as the acceleration, conceptually anyway, as the net force. We say it's directly proportional to the next force. It's in the direction of the net force, but it's inversely proportional to the mass. Okay, so they're tied in together. But this is probably the best way to think of it. You apply a force, and actually you need a net force. So in general, if you've got some object and you have, let's say, have a couple of forces, force 1 and force 2, then there'll be this net force that's off in this direction, and that's going to be the direction that the object's going to travel. So all of this is kind of just basic stuff that we're going to be playing with. There's also Newton's third law, which we'll pick up from time to time, is that forces always come from other objects. They're interaction between things. They're not just some invisible force field, although some of it looks a little weird, like gravity, where you've got this pull of gravity, and it's sort of, you can be up here, separated from the earth, not touching the earth, but yet it's still got a pull on you. Same thing like with magnets and the electric force. When we get into those later, those are going to be forces where we don't make necessarily a physical touching contact. Anyway, more on that, and about the only one we're going to be dealing with is going to be the force of gravity. In fact, the force of gravity, if you think about that, if we just have some mass and we say, okay, there's this mysterious force of gravity, we're not explaining what it is, I'll go to F sub g, and if I got some mass there and I drop it, this is one of the first labs we did, was getting the acceleration of gravity, right? Anything that we drop, and it doesn't matter on the size of the thing, what happens, what is the acceleration? Usually it's 9.8, or we'll give it the symbol g to make it kind of stand out as a special case. And usually for us, of course, it's 9.8 meters per second squared. Usually we don't write a minus. We're going to pay attention to the direction of this force, and then we're going to use it in an example with signs set up the way we want to set them up. So the idea is, if we use Newton's second law, that F equals ma, and the there's only one force acting. This is the net force, and that in this case is the force of gravity is equal to the mass times the acceleration, and that acceleration is g. So we make use of this as the force of gravity. It applies to whether the object is at rest. If I just release this thing immediately, even though it starts from rest, it's going to accelerate with the acceleration due to gravity. And as it falls and it picks up speed, it still has got the same acceleration. So this, of course, is a mysterious property of gravity, but it's one that we're going to make use of. Okay, so this is just kind of basic stuff. Usually forces come from different objects. Here's an example. Let's say we've got something like an elevator car or something. And we've got, let's say, a bathroom scale here, and we're going to have somebody get on this thing and stand on the scale. In general, we say, okay, gravity is going to be pulling down with mg. Let's say the elevator car isn't moving. There's going to be a force from the scale up on the person, which is what we'll call the normal force. Okay, and this normal force, in this case, in static case, would just be equal to mg, right? Now, what's going to happen is that the scale, the idea of the scale pushes up on the person. Newton's third law says the person pushes down on the scale, and so the reading on the scale is what we call the normal force. Now what happens if we're going to accelerate upward, and let's say we want to accelerate with some acceleration a. As we do that, if we're going to do that, we need to have an unbalanced force. I have to have more normal force than the weight of this thing to get this thing to accelerate. And the idea is that the sum of the forces, in this case, I'll call up positive, so it's going to be the normal force minus mg should be equal to the mass times the acceleration. The acceleration would be that of the car. Now, if you look at what the normal force is, that's equal to ma. Moving this over here is going to be a plus mg. So you could say the actual reading on the scale is something we call the apparent weight. So in an elevator that's accelerating upwards, you feel heavier. You're not actually heavier. The pull of gravity is still mg, but since the normal force is pushing up, you push more on the scale, and so your scale is going to read more. It's going to read not only your weight, but it's also going to read that kind of acceleration into it. So here's an example of two forces. One the idea of the weight alone, or in conjunction with another force like the normal force. Let's do another example that's kind of in homework kind of stuff. Let's say we've got a couple chords at different angles. Theta 1, this is theta 2. This is very similar to the homework problem you had, and maybe you have something hanging here with some force of gravity. And we want to get the tension, let's say, in each of these cables. Tension 1 is equal to something, and tension 2 is equal to something. We want to find out what that is. And we can use Newton's laws to get at this. When we're doing problems, it's important to know where to kind of focus. Newton's laws apply to all things. Now, this is a case that we call static, where nothing is moving. And so what about the forces? If there's no motion, then what can we say about the acceleration? That has to be 0. And what about the net force? Has to be equal to m times a, but that's 0, so the net force has to be 0. So anytime there's no motion, or could happen also if there's no I should say if there's no acceleration, to be more precise. But this is a case where this is just hanging here, and if we want to get the readings on these scales with this thing, I need to know where to focus. And what I'd like to do, and this is where experience comes in, I would like to focus on a little tiny, kind of a knot that's tying this together. And I can look at the forces that are acting on that knot. I would have the force of gravity pulling down, and I think it's pretty obvious that this is going to pull down with the force of gravity. We're going to have this cord, which is going to have some tension in it. Call that T1. And then off in this direction, I'll have another one. I'll call that T2. And I want to be able to resolve these forces. Now, the thing is with tension, usually we'll just say, what is the tension in the rope? Well, okay, I've got some tension. Which way is it pointing? Yeah, opposite of each other. Yeah, if I've got a rope, the idea of the tension, there's a lot of places we could focus. We could focus up here. I expect that this tension should be the same that it pulls from the ceiling, and also this one is also T2. So as you get looking around here, there's a lot of places to look. However, I'm still going to focus on this as far as being able to do the problem. It's all true that the sum of the forces on all of these pieces have to add up to 0, so the thing stays stationary. But what I'm going to do is set up and sum my forces. And the way I'm going to sum them is they better add up to 0. So I'm going to put, let's say, my x-axis like this, my y-axis like this. And then I want to do the sum of the forces, and I expect that the sum of the forces have to be 0 in both the x and the y. And what I'll do is I'll break these tensions up into components. Now, breaking it up into components, keep in mind that the tension itself is going to be along the hypotenuse. So if I'm going to do the components of that, imagine putting a little box around it squared with my axes that I choose. And I'm going to have, this is going to be T1 in the x, and there'll also be a T1 in the y. And this one I will also break up into components. A T2 in the x and a T2 in the y. A little sloppy here. The angles. We stated the angles up here, but hopefully your geometry is good enough to know that this is, our x-axis is parallel to this, and so that this would be theta 1. And then over here, this would be theta 2. That's a kind of a mess, isn't it? Let me write it out and see if you agree as far as my statement. I want to do the sum of the forces in the x direction. I'll do that, and I expect that there's going to be a T2 in the x. Let me do this. I've got T1. I'm going to take it, I want to get this side. And now, when we get doing this, a lot of people get confused about how to handle their trig. Let me talk about that for just a moment. We're going to be dealing with a lot of right triangles that get flipped all kinds of different ways. A lot of people have had their experience with trigonometry, and in trigonometry, you do something like the x and y axis, and then you do something with the unit circle, and then you say, okay, I've got some angle theta here, and then you learn that, on the unit circle, this is the sine of theta, this is the cosine of theta. What I want you to do from that experience, look at this as with a right triangle, that the side opposite that angle is the sine. We say the side adjacent, that is where this little angle thing hooks onto, is going to be cosine theta. And the thing is, when with the physics, we're going to be flipping things all kinds of different ways. I'm looking at this T1 as a triangle that's flipped back this way. I want to get T1 in the x, and so that's the side that's adjacent to that little angle. So I'm going to say that that's going to be times the cosine of theta 1. However, also, that's just its magnitude. It points in the negative direction. So I put in a minus sign. Okay, little things that to watch for. T2 isn't too bad. T2 times, again, the cosine of theta 2 would be the component this way. And now that's pointing in the positive direction. So anything pointing in the plus direction goes in as a positive. So that's going to be T2 times the cosine of theta 2. And all of this should be balanced. It should be 0, add up to 0, because it's not moving in the x. It's also not moving in the y. So we'll do the sum of the forces in the y direction. That's going to be, I've got, pointing up, I've got T1 in the y. That's equal to the side that's opposite the angle. So I'm going to go T1 times the sine of theta 1. That's up. Also, T2 is up. That's going to be plus T2 times the, not the cosine, but the sine of theta 2. And then we also have the weight of this thing, F sub g, pulling down. That's minus F sub g. And that's going to be equal to 0. Now, I guess we need to know some things here if we're going to solve for this. So let's just make up some numbers here. Let's say this is going to be, well, it looks sort of like 45 degrees. And let's just make up some numbers here. Let's say this is like 30 degrees. And so we can go ahead and put this in here. This is going to be minus T1 cosine 45 degrees plus T2 times the cosine of 30 degrees. Of course, we can stick those into the calculator, and this is going to be T1 times the sine of 45 degrees plus T2 times the sine of 30 degrees minus F sub g is equal to 0. Okay, so we've got some numbers. I don't want to get too caught up in the details of the math, but the big thing you want to keep in mind is we really have two equations. And I guess I would need to know something about that weight. Let's just say, oh, it's 100 newtons, just to make something up. So I say this is a minus 100 newtons. And then if you look at this, we really just have two unknowns. I've got two equations, but I don't know T1, I don't know T2. And also in this one, I don't know T1, I don't know T2. Now, your math should be good enough that you say, oh, I got two equations, two unknowns. They're linear. They should be pretty straightforward. And I'm just going to leave you with, okay, how would you solve for those tensions between those two equations? And your math should be sufficient to be able to handle something like that. So I just wanted to kind of touch on this as a class of problems where we call this an equilibrium, or sometimes called static, because it doesn't move. And the sum of the forces in both the x and the y have to be 0. So that allows for two equations to come out of this thing, and so you can solve for up to two unknowns. Okay, so we're kind of looking at different types of forces. I was talking about originally just the force of gravity, something falling, the idea of a normal force of a surface pushing on something, affecting the apparent weight. This is a case of tensions, and again, in terms of tensions, usually for a rope, we'll just say, oh, this is tension, like T1. The direction it applies is wherever you're going to apply it to. You want to look at the magnitude is T1, but it's in a particular direction. And draw it carefully as a free body diagram. I'm a bit crammed here, I realize, and probably a little hard to see, but I think you've done enough of these, at least on your homework, that you should kind of know what's going on with that. Let's look at another type of force that we're dealing with. One is a frictional force. And if you think about a frictional force, you've got maybe a surface that's not really smooth, if we could look at it under a microscope. And then I've got some kind of object here that it too isn't smooth, but maybe it's a little rough. And then you've got these two surfaces kind of pushing together. That pushing together is, one is the weight of this thing, and then this surface pushes back with the normal force, and those two things are going to be equal here. But if I push on this is kind of a case that's a lot like this. If I push on this cabinet, it doesn't move. Does the cabinet push back on me? Okay, and now if I push on it with just a real light force, let's say 1 Newton, what force does it push back? 1 Newton. I push 10 newtons, it pushes back 10. 100 newtons, it pushes back 100. What's going to happen here is if I apply a force, let's say I apply a 1 Newton force on this thing and it doesn't move. What's happening is these things are kind of digging in and they're kind of pushing against one another, and I push with a particular force and it pushes back with 1 Newton force. So friction would be equal to 1 Newton. If I push with 10 newtons and it still doesn't move, the frictional force would be 10 newtons. The idea that friction, this is something we call static friction because the object isn't sliding here yet. We say the static friction is less than or equal to, it's an inequality of some coefficient of static friction, which depends on these surfaces, what they look like, and then times the normal force. The normal force is going to tell us how much these surfaces are pushed together. And the more they get pushed together, the more we have to, a larger force we have to apply in order to get it to move. It can go from anywhere from 0. If I don't push on it, nothing pushes back, and that frictional force is 0. So it can go anywhere to 0 up to some maximum value. In a lot of the problems we're going to be dealing with, the friction, we're right at the verge of what we say slipping. And this would be the static friction, I'll say, is at its maximum value, would be where it's just equal to mu sub s times that normal force. Okay? The idea is there's going to be a limit here when these things are kind of caught together. If I push with enough force, it'd be actually just an epsilon more than this. This would imply that it's at its maximum value, but it hasn't slipped yet. Once I get it to slip, then it's going to go from static friction into kinetic friction. This thing is going to start to shave these things off, and it's going to slide along the surface. And so this static friction will become kinetic friction. And that's where these surfaces are just kind of sliding on one another. They slide. And actually, we'll model kinetic friction is usually fairly simple. It's just going to be equal to mu sub k times whatever the normal force is. And it doesn't matter how fast this thing is moving, this kinetic friction is going to stay the same. Now, you might say, well, this is a little flaky, and you're absolutely right. Friction is really a complicated thing. And if we have like oils or lubricants here, things can get very complicated in the motion. However, in the problems we're going to deal with some fairly simple types of friction. One is, of course, the static friction where the two surfaces don't slip on one another. And the other, the kinetic friction, where the surfaces do. In a little bit, we'll also talk about air friction and those kinds of resistances. So we'll build a little more sophisticated model of friction. But all of this stuff is really approximate. You don't want to think of this as sitting up at the same level as F equals ma. This is a bit on the flaky side. Usually, the coefficient of kinetic friction is less than that of static friction. For instance, if I pull this thing, it slips about 10, and then it drops back to about 7. So usually, this coefficient of kinetic friction is usually much less. Mu sub k is less than mu sub s in doing problems. So. Okay, So I'm just kind of outlining some of these basic forces. In fact, let's take a look at number 1 on these practice problems. Yeah, I've got practice problems. I hope everybody got them. They're up front here if you haven't gotten one yet. So number 1, we've got a surface. We've got a block that we're going to be applying some forces to. I like doing these forces in red. We're going to be pushing down on this thing with respect to, so I'll push with a 35 Newton force. And there's also going to be, this is 7 kilograms is the size of this thing. There's going to be, of course, gravity is going to pull down. So that's going to be mg. Well, let me just write mg for that. There's also going to be, this surface is pushing up with the normal force. Okay? Always forces between things. mg is the force between this block and the deep earth where it is pulling this thing. The normal force is this upward one from this surface. Now this surface also applies a force that's parallel to the surface. The idea that if I'm pushing on this like this, it's going to want to slip this way. If this, think first in terms of if this is a real slippery surface, this slides easily. Friction always wants to fight that motion, so I expect that friction is going to be back in this direction. And in this case, we've got the coefficient of friction. Now, he does ask for us, the surface has a coefficient of friction of 0.20. In fact, we can look at, just a little detailed look at the frictional force is going to be kinetic friction because apparently this thing's going to slide. He wants to know what the acceleration of the box is. So that is a slipping motion. So that should be equal to the coefficient of kinetic friction. That's going to be 0.25. And we're going to multiply that times the normal force. You want to be careful not to make it the weight, but I want to come back to this equation in just a minute. What we first want to do, we want to come up with some of these forces. Now, I've got a 7 kilogram block, so it's easy to get this 7 kilograms times 9.8 is meters per second squared. That's going to be the weight of this thing. I've got 35 newtons down. Now, what I'd like to do is do some forces on this thing. Let me do this work over here. I expect this block to slide along this axis, and this, I might as well call this our x-axis, and then the vertical would be the y-axis. And so I do expect it to move in the x, but I don't expect it to move in the y. So maybe I'll start with that as kind of the simplest. Some of the forces in the y are going to be, okay, now I've got, of course, gravity is pulling down, the normal force is pulling up. This force I probably want to break into components. One is a downward force. This is, that's a downward force. This is a force in that direction. So this 35 Newton force can be thought of one in the x, one in the y. That angle, there was a 30-degree angle. I didn't label that. 30 degrees. So let me look at the sum of the forces in the y. I expect this 35 to have a downward component. So this is where I'll put in the minus. That's going to be 35 newtons times, I want the side opposite the angle. That's 30 degrees. So that's going to be times the sine of 30 degrees. That's downward. The normal force is up plus n. I've got the gravity is down. Let me just leave it as minus mg. And then all of this should be equal to 0. Now, what this will allow me to do is solve for the normal force. Let me just take these two negatives over to the other side, and I think it'll be more apparent. N is going to be equal to 1. It's going to be equal to the weight, mg. But it's also plus 35 newtons times the sine of 30 degrees, which is 1/2. The big thing is the normal force is greater than the weight. We are also having to deal with the fact that we're pushing down on this block. So let me use this block as a kind of a prop. The idea that I'm pushing down on it, the fact that I have that component in addition to the weight of this thing pushing down on the table has to push back with a greater force. That affects the force of contact between these two surfaces. It's going to be, that force of contact is going to be more than just the weight of the object. It's due to the fact that I'm also pushing down on it, and it has to push back in order to keep this thing from moving. So that's kind of interesting. Then when we get to the sum of the forces in the x direction, that is going to be, here I've got a component that is in the x. That's going to be 35, and let's see, that's the side adjacent to the angle. That's times the cosine of 30 degrees, and that's in the positive direction. Friction always is fighting me. That's going to be minus the frictional force, or 0.25, times whatever the normal force is. That's back this way. And let's see, any other forces in the x? I don't see any. mg and the normal force are in the y strictly. In the x direction, then I set this thing, what do I set it equal to? 0? The sum of the forces, F equals, yeah, ma. And that's what he wants to actually find. He wants to find that acceleration. So that is really the question that he's asking. I've got my notes. I don't want to take time to stick in all the numbers here. We do have the mass, and we know g, so we can certainly come up with a number for the normal force, whatever that is, and then we can make use of that back down here in the x direction. We can put it in there. I've got all the other things, and then I can immediately do some algebra and solve for the acceleration. So, okay, so that's kind of an example problem like this. And again, you want to watch it carefully. If this block was just sitting there with no forces applied to it, I would expect the normal force to be equal to the weight of this thing, mg. But again, you push down on it, it pushes back, and that just pushes these surfaces more tightly together, and they won't slip as easily. Okay, let me do just kind of a motion problem that is somewhat generic. This says these forces, I'm dealing with a single object. And here I choose a little single object at very specific point. Let's take a look at a system of things. Let's say I've got a couple objects, and I'm just going to do this generically. I don't have it as one of the practice problems, but I think you can see it all right. And I did. Okay. And so I'm just going to do it kind of symbolically, and hopefully you're okay with that. I've got, let's say, an inclined plane, and right now, let's say it's frictionless. There's no friction. There's going to be maybe a massless, frictionless pulley up there, and I'm going to connect it to some mass. I'll just call this M1. I want to just kind of do this generically. I think sometimes it's easiest to kind of see more what's going on if you're not looking at a bunch of numbers. So this would be M2. And let's say, well, I want to release this thing, and I want to be able to get the acceleration of this. They're going to take off. One of the first things I need to do is decide, I want to set this thing up. First of all, which way is this thing going to go? Yeah, it depends on the masses, right? You might, if this is really heavy, it's going to go flying. If it's heavier than this, however, if this is real heavy, it would maybe pull it the other direction. So I'm not sure. The math will tell us which way it's going to go. What I would do, and there's lots of ways of doing problems, but I think this is the best way to stay out of trouble with these two-body problems, is that they are tied together and they're going to move together. You know, when this one goes down, this one's going to go up. Or the other way around. I would decide which way you want to call positive motion for this thing. Let's say if this thing goes up, let's say that's positive. Well, if that goes up, this thing has to go down, and so I'll call that positive motion. And that's going to set up my sign convention. Then I can look at the forces that are acting on these things. Now I could draw separate free bodies. I'm going to just use colored on top here, so I think I can avoid that in this fairly simple case. I'm going to have an M1G. I'm also going to have some tension. Now think of this tension again, it's applied, depends which end we're talking about. The tension in this cable is going to pull on this one in this direction. I'll just call that tension T. There's going to be a normal force. I'll just call that, let's say, N1. And then it's tied over on this one. This one, gravity is pulling down with M2G and pulling back with tension. And I do expect these two tensions at the end of the rope to be the same. Really, ideally, that's due to a massless, frictionless pulley here. These are just ideal pulleys. Later on in the course, we'll deal with real pulleys, and then these tensions can be slightly different. But that's a way for the next section that we'll be getting into. Okay, so then I can actually do the motion for this thing, and I'm going to do this for this one. This is the plus direction. I can call this, and I can label these axes separately. I'll just call this the x-axis, if you will, and then this would be the y-axis, and then I'll have this motion strictly in the x. This one is going to go down. Whatever this one goes up, this one's going to go down. So it might be handy to even call this x instead of y. And this would be the plus direction. So if this one goes up a distance x, this one goes down a distance x. And then they represent the same thing. Okay, now let me do the sum of the forces for this one. Sum of the forces on the first one in the x direction. That's going to be the tension is going to be pulling. I've got gravity pulling down a little bit. Excuse me, I didn't specify this angle. This angle theta is, let's see, this might be let me draw a separate diagram here, since this is a sticking point for a lot of people. If we have some object here and gravity is pulling straight down, mg, and that would be in the downward direction, and I want to get at, let's say this is some angle theta. I want to be able to break this thing up into components, and the way I'm going to break it up into components are going to be along the surface and so on. So I'm going to want to have a normal one and then also one back in this direction. Now, as seeing these angles, if this is theta, you can think of this, look at this as being a right triangle here. This is going to be, let's say, alpha. And these are going to be complements of one another. That is, they add up to 90 degrees, since this is already 90. That should be the same as this angle. And so what I would contend is that this angle is going to be theta. Now, I would suggest that if you're having trouble with this, take the time to draw a large, accurate drawing to sort this out. It can get confusing. We have a lot of right triangles. We flip them different ways. This one is like this. It's flipped like this. We want to be able to sort out those angles. We want to be able to do it, and we want to be able to do it quickly. One way to look at this, which can be helpful, is to look at a change. For instance, if this is the horizontal, this is the vertical. If I take and imagine rotating this thing, this green line through angle theta, since on this plastic, what about the red line? Doesn't this also rotate through that same angle? And if you can see that angle that it's going to rotate from the vertical is going to also be theta. Now, one way you can sort this out is imagine this rotation where this gets to be smaller. This angle gets smaller, but alpha, this other complement, would get bigger. As that gets bigger, of course, that gets smaller. So if you can see this, I hope it makes a little bit of sense if you can see it in terms of this rotation. Again, here the normal is like this, rotated like this, means that this angle pointing up, I guess I've got to, maybe it'd be better to draw it this way, where it points straight down. I rotate this through an angle theta. Well, now this one is from the vertical to that is also that same angle. Does that make some sense? Some people can see that right away, and it can be of great help. Others, you have to kind of go through the geometry of this. But I'm going to make use of that here because I need to break this up into components, and I need to be able to do it accurately. If this is theta, then I expect this to be the alpha, and I expect this angle to be theta. And so mg, and I want the component this way is going to be mg cosine theta. The component down the incline, which is this, is going to be opposite that angle. And so I'm going to say that as I write this out, it's going to be t, and then I'm going to have in the negative direction, a minus m1 g, and it's going to be times the sine of theta, that angle opposite that. And that should be equal to this one's mass, ma, m1, times the acceleration of the system. So this would be like the first equation. Then I can look at this object here. Maybe I'll do this over here. Some of the forces in the, I'm still calling it the x. Keep in mind that I call down positive, so anything pointing in that direction is positive is going to be equal to m2g, and then minus the tension, and that should be equal to this one's mass, m2, times its acceleration. So this would be the other equation. So one of them for each of these things. I do have them tied together so that they're moving together. Then what I typically want to do is maybe solve for, if I want to solve for the acceleration, I'd maybe solve for the tension. So I could get the tension, solving this, I'll take this over to the other side, m1a now plus m1g sine theta, and then I can take that and put that back up into here. So I'll have m2g minus the tension, m1a plus m1g sine theta. Get this picture out of the way. Okay, so m2g minus, that was the tension, is equal to m2a. If I want to solve for a, I want to get the a terms together, so I'm going to be left with m2g, now a minus m1g sine theta. and I'll take this over to the other side, is going to be an M2A, and now a plus M1A, and so I can factor out an A and divide through by M1 plus M2. There's M1G sine theta. And I've got a general expression. Of course, yeah, a lot of students, they want to see this with numbers. Make up your own numbers. Go ahead and put them in. They do. Now, the acceleration will tell you what direction this thing is actually going to go. I was assuming that this is the plus direction. So if I get a positive acceleration, it is going to be going in the positive sense. And that would happen if this term is bigger than this term. Then this whole thing would be positive and it would be going this way. Basically, if M2G is more than the component pulling this way, it's going in the positive sense. If this term happened to be bigger than this one, then that minus sign will automatically tell me that that acceleration is negative. It's going to be going the other direction. And so the math will kind of tell me what's going on. Okay, in general, the big picture here is these are two objects that are tied together. They move together. It's best to have their coordinate systems together. It saves a lot of sign errors that can really come in and haunt you in a problem like this. And then you deal with your free body diagrams for each one of these things. And they will be tied together. They have similar unknowns. If we do happen to know the masses, the thing we don't know is the tension. We don't know the acceleration. We have that one. On this one, we don't know the tension, and we also don't know the acceleration. So again, it's two equations, two unknowns. I eliminated the tension and just went for the acceleration of that system. Okay, so that's kind of a generic problem. You've got some homework ones that are like that. And yeah.
So why do you have two FNet X's over here?
Oh.
FNet Y.
Oh.
Yeah, like why is it T minus or M2G minus T on the right side?
Oh.
Yeah, why do you use that?
Okay, yeah, okay, that has issue to deal with this direction that I want to call positive. Now, these are going to be tied together. Now, you don't have to say, you could say, well, I want to call this one plus going up, and they say, no, I want to call this one plus. Well, you can do that, but then you would have an acceleration, let's say, of this one, A1, and this one would be going the opposite direction. We'd have to set that as a minus A2, and we'd have to label these. This can lead to problems. That's why my suggestion is first thing when you get this thing, take a look at it, decide which way you want to call positive motion. I call this direction plus to do it. I could have labeled it the other way, wouldn't have been any problem. But if this guy is going up, this guy has to be going down. So for both of these, I'm calling this direction positive. That way, when I talk about acceleration, I can be talking about the two. They are tied together. When this one goes up x, this one goes down x. They will also be tied as far as their velocities and also their accelerations. If this is accelerating that way, this one's accelerating that way.
So what you're saying is you rotated the coordinate plane from, I guess, the diagonal one?
Yeah, you can give them separate names if you want. It might have bothered you that I called this one X and also call that one X. Okay, give it another name. You could call it, you can go ahead and call that Y. And then I should say a negative Y. And then you would have called this force in the Y, and that's okay. But again, I'd stick with this sign convention of keeping these together. You can name this one X and this one Y. It's okay, or call them both X. Or call this one X1 and call this one X2. Maybe that'll be help a little bit. But once you set those directions, that was key for getting my signs right here. Yeah.
For that part, so I'm having trouble understanding how you assign sine or cosine and an angle. Is it just so taught telling figuring out the relevance?
Okay, I tried to allude to that here a moment ago as I tried to draw that bigger. This is kind of small and admittedly confusing. It's again, let me sketch this again a little bigger because it is a difficult one to see. And little note also, there's a tendency when you're in the exam, you want to maybe do a sketch. That's a good way to do that. You're going to do free body diagrams. Beware. There's a tendency particularly when you're in a hurry, to make all your angles and they're all 45s. And then you can't tell your sines from your cosines. So always kind of exaggerate it a bit. In fact, for this one, let me exaggerate that even more. Let's make this angle, clearly less than 45. And then this block that's sitting on here, let me just kind of get the relevant thing, is the gravity is pulling down with mg. We want to break it up into components. And one of them is down the incline, and of course the other one is off in this direction. But the idea that these angles, use this orange here, this will be theta. This one here is the complement of that, because this is a right triangle. Can you see that well? And this one will be theta again.
So it's from the vertical down, not from gravity.
Yeah.
J squared.
Yeah. Right, and if you can kind of see that if we made this, imagine this thing coming down and theta gets smaller. This angle will also get smaller. They're going to go together. Can you kind of get a sense for that? If you were rotating this thing, this line would come down, and then these angles would get smaller. It really helps to do a careful drawing and kind of get it etched in your mind, because we do take these triangles, we kind of flip them all different directions, and it's real easy to kind of get that mixed up. It's a real common problem. Okay, so I hope that helps a little bit. If you're still stuck with that, maybe see me afterwards. We can work on that. And but partly my pictures are lacking trying to do them on the board. A real accurate one, I think it would be a little more readily apparent to you. Okay. Anyway, as far as on this, again, determine which way you want to call positive. Then when you lay out your vectors, you put this one's t, this is positive, this one is negative. Over here, this is positive, this is negative. And you mess up your signs, you're going to mess up the solution. Okay. We also dealt with some things with circular motion. The idea that if you're traveling in a circle, let's say just a simple example would be something like a ball and a string. You're whirling around, and that ball is coming around like this. And that ball, we have a string, and you'll notice that this string or this cord is pulling in on the ball, and I expect that there will be a force in on the ball. The thing is, we very often want to describe this really gets in the way of our intuition, that when I'm swinging this thing around, I feel an outward pull. Okay, and that's where people swear, no, there's something pulling out on the ball. But what it is the tension in that cord is pulling out on my hand. This is action and reaction. When we do problems that are for circular motion, we have to focus on the object that we're dealing with. In this case, it would be the ball and the forces that are acting on the ball. What I'm feeling is the reaction force. And so I do feel an outward pull. but it's not the action, it's the reaction. I want to focus when I do problems on the action on the ball itself. Okay, now let's, well, this is a good one, good way to start. Suppose we're going to go on a roller coaster. And okay, and this roller coaster, let's say it goes up and down, and just for convenience, let's say this is more or less kind of a circular path that it's on. And up on top is going to be this roller coaster car. And let's say we want to get it traveling with its maximum speed, that it can still stay on the track. So the idea is, what is Vmax? And the idea would be, let's say if the car was just sitting there, gravity would pull down, mg. And what about the normal force? The normal force would be holding this thing up. And now if it's going to be going on a circular path, let's say you're not quite up to the maximum speed yet, we'd say some of the forces, I like some of the forces in the centripetal direction. I like saying, okay, the acceleration for circular motion has to be into the center. So I want to call that the positive direction. So mg is in that direction, so I'm going to put that in as a plus, okay, and then minus the normal force, and that's all the net forces. It should be equal to ma, the mass times the acceleration. The acceleration, since it's traveling in a circle, has to be v squared over r. Okay, now let's say we want to go faster and faster and faster. As the faster we go, what's going to happen to the normal force as we go faster and faster? Yeah, it's going to tend to be zero. That is, in fact, if we're going along this thing and we're going to actually start to lose contact with the track, we could have the normal force go to zero. That would mean that the wheels aren't actually even touching it. It might be just gliding over that roller coaster and still on a circular path following the track, but it's starting to lose contact with the track. That's going to happen when we're at, let's say, the maximum speed. And then I can solve for that. Let's see, the m drops out, and I can go gr is equal to Vmax squared. I'll take the square root. And this would represent the maximum speed that I could go and still kind of stay on the track, but really about to lose it. The normal force goes to zero. What if you're sitting inside this thing on one of the seats? What about your normal force? Goes to zero. So and what about the floor of your stomach? Goes to zero. You're effectively in free fall. So that's that feeling you get in the pit of your stomach that you are, in a sense, dropping. The car is dropping around this thing. There's no normal force. mg is just acting. Literally, you're shooting out to the side and dropping down. If you're traveling even faster than that maximum speed, you're going to go flying off into space and be a projectile as you go off the curve here. Okay. How about if you take that same speed and somehow there'd be a natural tendency that the roller coaster would pick up speed, but let's just say you're on the bottom, maybe you put on brakes a little bit, and you're still traveling at the bottom of this thing with a velocity that's equal to that, so you're basically the same speed at the bottom of the hill. Then I say, okay, this is a circular path. Let's say the center of the circle is up here, and I look at the picture here. This is going to be, of course, mg is still down. Now you're kind of plowing into this thing. You'll definitely have a normal force here. And then you can do the sum of the forces in the radial direction. This is going to be the normal force in minus mg coming out. And that should be equal to the mass of this car times the the acceleration. The acceleration has to, it's traveling in a circle, so it has to be v squared over r. And we can solve for that normal force. That's going to be equal to mg plus mv squared over r. And, v, if I go ahead and use this for v, that will be mg plus m over r times v squared, which is the square root of gr squared. Okay, that's going to get rid of the square root. And we're going to be, wait a second here. What am I doing? I'm screwing something up. Never mind. Let me try that again here. Okay, I'm going to plug this in. V squared just gets rid of the radical. So that's going to be equal to mg plus m over r times v squared, which is g over r. The r's go out, and we have mg plus mg is 2mg. Okay, so that's the normal force. Now think of yourself as sitting on like a bathroom scale there. What do you feel? That would be your apparent weight. You now are no longer weightless like up here. You actually have, really your apparent weight is twice your ordinary weight. So you're experiencing what we call 2 G's of force down at the bottom of this thing, traveling like that. So, okay, a lot of things kind of illustrated here. I wanted to talk about circular motion along with using these other things like the normal force and of course gravity itself. Yeah.
Can you go over again why the normal force becomes 0?
Oh, 0. We are going to go faster and faster. For instance, let's say I take this, let me solve for the normal force. The normal force, I'll take this over to the other side, is equal to mg minus v squared over r. Okay, so the idea is if we can go faster and faster as that gets bigger, and it keeps taking away from the weight. So in the extreme, let's say you just have the elevator car and it's just sitting up on top, not moving at all. You sit in the seat, and of course gravity pulls down and it feels like mg. You're a normal weight. As you get moving more and more, this is going to be taking away from your apparent weight. And when you get up to the maximum value is when we say just when this thing just goes to 0. Okay. Now if you go faster than that, you would lose contact with the tracks, and still since you're not touching the tracks, it stays 0. So it's right at that where you just start to lose it and go over.
Thank you.
Yeah. Okay. I want to get back to doing a problem, but I want to first deal with motion in a circle. I want to get to the banked highway problem, which I think is number 3. And I want to say something first before I do that. Number 3, Caltrans wishing to build a banked highway. Or maybe I'll just launch into that. This is going to be number 3. Okay, Caltrans wishes to build a banked curve on a new freeway interchange. The radius of the curvature needs to be 200 meters, and he wants to know at what incline should the road be built for safe travel at 55 miles per hour. Safe travel being defined as 0 friction traction needed at a speed. And he gives you a conversion, so you can do a conversion on that. In fact, let me do that. Okay, yeah. Okay, let me launch into this thing. We're going to have this banked highway. Now, what I want think of this car going around, and this circle like this. So we're kind of doing a horizontal view. And the banked highway is sitting at some angle, and we're going to want to find that angle. And the car is going right into the board here. So we're looking at the car, tail lights and so on, and it's going into the curve. The center of the curve is back this way. Since you're going in a circle, there has to be an acceleration. And I don't want to confuse that with a force, so I'm going to put that in green, that acceleration has to be v squared over the radius of this turn, where this would be the radius of the turn. Okay, now there's really going to be only two forces that are working, hopefully for us. One is going to be gravity, that's going to be straight down, mg. And then there's also going to be a normal force that is going to be perpendicular to that surface, n. And really it's that normal force that is providing for a component of force in the radial direction that's coming into the center. Let me do another little thing here. Okay, now what we're going to do is in the y motion, I'm going to break it up into an x, or maybe instead of calling this x, I want to call this the radial direction, since it's going to be on a curve. The vertical we'll call the y direction. Now the idea that you're going around this thing, if you're going just the right speed, we will have the normal force, and we need to solve for that to give us an acceleration into the center. We don't want to have to rely on friction at all. So if this is icy conditions and you're traveling at a velocity of, what did he say, 55 miles per hour? I did a real quick conversion. It'll be easier for us to deal with that. I've got that is equal to, and you can, I'm sure, verify, 24.58, and that's in meters per second. Okay, that'll be just a little more convenient to deal with. And what we want is, we want the car to stay in its lane. Now if it's staying in its lane and not skidding out and going out this way or sliding down this way, it's going to maintain the same y altitude as it goes around this curve. So what I want to do is get the sum of the forces in the y direction. I want those to be 0. Now, in the y direction, I'm calling it straight up and down. Notice I didn't bank my angle, my axes. I could have done that, but I'm following the same way they're doing it in the book, so you can follow it easier. We're going to have mg is going to be down, minus mg. We've got a normal force up. Now, here we're dealing with that angle stuff again. As this theta gets bigger, this angle will be theta. Maybe try that argument one more time here. This one might work. As I rotate this through angle theta, vertical is straight up for the red one. It goes off, and that matches this normal force. So again, it's sitting at an angle theta from the vertical. And I'm going to break that up into components in both the x and the y. Again, I'm going to break it up this way. This is going to be force, normal force in the x, and then I'll also have a normal force in the y. In terms of these numbers, again, I've got mg down. The normal force in the y is going to be this component, the side adjacent to that, so that's going to be plus n times this cosine of theta. Now that should be equal to the mass times the acceleration in the y, but that's got to be 0, so we've got that. And let me come back to this one. Let's do some of the forces in the radial direction. In this direction, I just have one. mg is straight down. I've got a component of the normal force That's going to be n times the side opposite here. That's going to be times the sine of theta. And that should be equal to mv squared all over r. What I can do in this one is I can solve for the normal force. I'll take mg over to the other side. N times the cosine of theta is equal to mg. And divide by the cosine of theta. So a normal force is mg over the cosine of theta. I'll use that and I'll plug that into my y equation. So I'm going to have an mg, and I've got a sine, and I'm going to have another cosine. This is going to become the tangent of theta is equal to mv squared over r. Now, something's interesting. You notice the mass drops out. This is very handy because when we're designing this thing, this could be any massed vehicle. It could be a motorcycle, cars, trucks, semis. It doesn't matter the size of the thing. The math works out the same. And so we can solve for the, let's say the tangent of theta is going to be v squared all over gr. Would be my general expression. Of course, if I want to get the angle, I take the inverse tangent. So inverse tangent of v squared over gr would be the solution for that. Okay? You've got a homework problem. I don't think he'll do this on the exam because it gets a bit involved. One where a range of speeds, if you're traveling too fast, there's a tendency that you want to skid out, leave your lane, and collide with the guy next to you. In that case, what you need is you do need some friction. The way we've designed it right now, we're not even using any friction at all. But if you are traveling faster than that speed, faster than the 55, let's say you're traveling at 65, you're going to need some friction, and that friction is going to be down the roadway, along parallel to this. And so when you're doing that homework, you put the frictional force down this way. If you're traveling too slow, if this was icy conditions, you would tend to slide down the incline, and then you would need that extra frictional force to be back in this direction. So if you've tried that, it's a good problem, but it's pretty involved. I don't think he would do it for the exam, but it's a good one to maybe look at. Okay, so those are kind of some examples of circular motion. We'll come back to some more in a bit here. Where are we at? 2. Okay, let's we'll take a break in a minute here, but let's do one more issue I think would be best before we take the break. This is actually comes in chapter 6. In fact, we're kind of doing 5 and 6 here. 6 had this stuff with circular motion that we're dealing with. Chapter 6 also dealt with like air friction, and this has shown up fairly frequently in the exam, so I think we want to look at it. And I've even got a problem that we're going to be looking at. But let me put it over here. Okay. Okay, so air resistance. And we're going to have this resistance is going to be proportional, some proportionality constant of B, we use that proportionality constant, times V is the velocity. Let me help make some sense of that. We're kind of defining that. If you think, I mean, and it's fairly reasonable, if you think of like driving down the road, you stick your hand out of the window, you feel that pressure. The faster you're traveling, the more that pressure is holding you back. And so this is what this is saying. That resistive force backward is going to be directly proportional to the velocity, is the idea. There's another case, it could also be proportional to the square of the velocity, and we'll look at that next. But the idea would be is if at fairly slow speeds, this holds pretty well. And let's say I just start with some object, mass m, and we're going to drop it. And if I drop it, there's, of course, gravity is taking hold, mg. And right now, if the thing, that is, if the velocity is equal to 0 at this point, there is no resistive force at all. So it starts to accelerate, and at first it accelerates like a free fall, 9.8 meters per second. After it falls a little bit, it starts to pick up speed. Then you're going to have you're still going to have gravity acting on this thing, but the resistive force opposing that motion is going to be proportional to b times whatever speed you're traveling. Now, the thing is, if we're in free fall here, and the way I've got it drawn here, the resistive force is starting to grow, and the faster it goes, the more it grows. But at this point, mg is still more than that, and so the net force is still downward, and so it's still going to accelerate. It's going to pick up more and more speed. As it picks up more and more speed, this resistive force just keeps growing and growing. And then at some point, as it falls and picks up speed, then the idea will be that the gravity, mg, would be just equal to the resistive force. So the resistive force grows so that they're identical. Resistive force would be b and times v, and we're going to give a special name for this v at this point. We're going to call that sub t the terminal velocity. The idea would be that once this resistive force gets to be the same as mg, the net force is 0, and therefore it's not accelerating anymore. The acceleration is 0, and vt is this terminal velocity. And actually, from this, there's a fairly simple relationship we can look at. We can just say, okay, some of the forces in the y is going to be, well, let's call down positive, is going to be mg is pulling down, resistive force minus b terminal velocity is pulling back up. That is all equal to 0, so that there's no acceleration. And then if I solve for the terminal velocity, it'll be mg over b will be equal to the terminal velocity. Move this over to the other side, divide by b. And so that's fairly simple if you understand that basic idea. Now, what if he's not so kind? What if he says he wants to know something like, at what time is this thing at 1/2 the terminal velocity? Okay, something like that. Let's solve for this motion as a function of time. Now, if we go to do that, I can say, I'm going to kind of focus at this point. This is sort of the intermediate between 0 velocity and terminal velocity. I will say that the sum of the forces, and I'm just going to call down positive since it's obviously going down. It's going down. It will be mg minus bv. And according to Newton's laws, those are the two forces. The net force is equal to the mass times the acceleration. Okay? Now, we also know that the acceleration is dv dt. And I want to solve for this thing. Right now, this is what we call a differential equation. I'd like to solve for the velocity as a function of time. But I've got this nastiness here. I got v there, but I've got a dv dt here. So what we're going to do is we want to, like you would an algebra problem, we do it separation of variables. I want to get v is equal to something. So what I'm going to do is separate variables by, I've got a dv here, and I'm going to take this whole expression and divide through. And then on this side of the equation, I'm going to bring a dt. And then I've got that m. Well, let me leave the m on this side. Okay. And then what I want to do is I can integrate this thing. What I'll do is integrating my dt's is going to give me my change in time, which is going to be the time itself. Since at t equal to 0, I'm going to start this thing. So I'm going to start it at t equal to 0, go to some time t. That's going to give me that. On this side, I need to integrate m dv mg minus bv. This is a little trickier as an integration. I need to integrate that. I'm integrating for velocity, so it's going to go from 0 to, I'll just say, some velocity at some time. So when I'm doing my calculus, my limits have to match. This is with respect to time. This is with respect to velocity. And so velocity here matches some time t here. In doing the integral, probably u substitution. Let u equal mg minus bv. And I'll put that in. And let me take this m outside, and I'm going to have a dv. Well, let me deal with this u first. This is going to be u. I can look at this and solve for du. When I take du, this is a constant. That goes away. This is going to be a minus b dv. And let me solve for dv. dv is going to be du divided by minus b. Or let me put the minus up here. And then I can put that in over here for dv. I took the m out. I put in that. That's going to be a minus du over b. And let me take that b out and put it there. The limits, I want to be careful. I'm changing variables here. So when v was equal to 0, I'd go up to here, v equal to 0, that's equal to that. U is equal to mg. When v is equal to v, well, that whole expression holds. That mg minus bv holds. Okay, a lot of math here. Okay, and this is going to be t. Let me bring that minus sign out front here. Make that positive, so I've got mg. Let me take this over to the other side to join t. Minus bt over m. And then I'm just doing this integral. This is going to be the natural log of this thing on top, mg minus bv, all over mg. I can break this up. This is going to be the natural log of mg into that goes 1 time minus bv over mg. And then do another step here. I can get rid of the natural log by taking this e to the minus bt over m is equal to, when I take this to e to this power, I just get this thing inside, 1 minus bv all over mg. And I want to solve for the velocity, so what I'll do is I'll take this over to the other side, bv over mg, and I'll take I'll take 1 minus this, minus e to the minus bt over m. And then solving for v is the last step. Let me bring it up here to see it a little easier. I'm going to be solving for v. I want to take the mg over b over to this side. So I'm saying v should be equal to mg divided by b all times this whole stuff in the brackets, 1 minus e to the minus bt over m. Okay, and this is the general expression for the velocity as a function of time. Okay, now you can just remember that. It probably wouldn't be a bad idea. There's enough chance that he's going to ask a question like this that you might want to walk in on the exam like this, or you with that understanding. Clearly the math is a bit tricky, but I'm taking you through it partly in the next problem that we're going to look at, he actually expects you to do something similar, but the math is easier, and we'll look at that in a minute. Typically on something like this, if we were to look at the plot of this thing, the velocity as a function of time, it's going to be, we say, exponential. It's going to be increasing very rapidly, and it's going to approach what we call terminal velocity, and it's going to do it asymptotically. The idea that it's traveling faster and faster and faster, it never quite gets to this point. It gets close, but it actually just approaches that. A more typical thing is at what time? He might ask, what time is the velocity equal to 1/2 the terminal velocity? Well, if you ask something like that, something I meant to do here too, this mg over b, I got a little sloppy here. This was, mg over b was the terminal velocity. So maybe, screwing up my board here a little bit, but you can replace all of this in black with just v sub t, terminal. Is that too confusing to look at? All of that is the terminal velocity, vt. So what we can do is, let me write that form of it here. This is probably the best to remember. The velocity is equal to the terminal velocity times 1 minus e to the minus bt over m. And when the velocity is 1/2 that terminal velocity, these terminal velocities can just cancel, and then you need to, he'd have to give you in the problem something as far as what B is, that resistive force. But then, I'm going to leave it here as a math problem. This is a 1/2. You should be able to go in and solve for t, the time that it's going to be there. He has asked some problems also if you have velocity as a function of time, what's the total distance traveled? Okay, do you remember those problems from the last section? If you have velocity as a function of time, it's not constant. Can you get the distance as a function of time? Maybe I'll do that real quick over here. Okay, so again, the velocity as a function of time is the terminal velocity times 1 minus e to the minus bt over m. And we know that v is equal to dx dt. So if I want to get x as a function of time, I can integrate this. Okay, I want to integrate this. This is going to be, if I'm going to integrate this, vt 1 minus e to the minus bt over m. Let's do it as an indefinite just to kind of illustrate how this works. Okay, we go ahead and I want to integrate this thing. So this constant comes out. That's going to be there. Then I'm going to integrate, and I'm integrating with respect to time. I now have, so I take this outside. I'm going to have a 1. That should just become a t. Then I'm going to integrate this. I'm going to have, it's going to be a plus e to the minus bt over m. That is, when I integrate it, I'm going to have this thing back. But I've got to think, I've got to be able to take the derivative of this. When I take the derivative, I get this back. But then I get this. I'm going to have a minus. I'm going to get the minus that way. Minus, minus. That's going to become a plus. Let me put it down here and see if you're okay with it. M over bt, or just m over b. T would not be there. M over b. And yeah, so if I took this thing, again, I want to take the derivative. I will bring this down. This will give me my minus sign. It's going to leave behind the natural log. I've got that. And so x should be equal to that. But we should also have x as an integration constant, or I should have some constant of integration. I'll just say c. And I expect that that's, normally we'd say at t equal to 0, that's equal to x. But let's be careful. At t equal to 0, what is x? X is equal to, well, that's the terminal velocity. Well, this t is 0, but it's going to be plus m b e to the minus b 0, so that's a 0. What happens when we take e to the 0 power? That's 1, so I end up with the terminal velocity plus 1, which is going to be mb. Excuse me, that's vt times mb. Getting tired here, we're going to need to take a break. Plus c, that should be equal to x. Now if I want at t equal to 0, I want, let's say, x to be equal to 0. Then I'm going to have c will have to be a negative of that. So c would have to be a minus vt mb for x equal to 0. So our overall solution would be x, the distance we've covered, terminal velocity, times would be t plus mb over e to the minus bt over m plus c, or in this case it's going to be a minus vt over mb. Woo, I should have practiced that. Okay, so that's, wow, kind of a nasty expression, but he has asked that one. Okay, more typical of an example that he has given. All of this was with the air resistance was proportional to BV. And clearly this is, as far as mathematically, this is the nastiest stuff in this whole section, in this whole possibility of an exam. However, he has asked a question like I'm about to give you that has shown up quite often, and I think I need to warn you about that possibility. And it's one of these practice problems where I have the extra problems. These are a little trickier. That one single page here of the, just call it extra problems. And I don't even have the number. I mean it to be this number 1 of the extras. He's got a race car, a 1,000 kilogram race car crossing the finish line at 175 miles per hour. And he gives you the conversion. After crossing the finish line, the race car shifts into neutral, so only the force slowing the car down is air resistance. Now he says the air resistance is F is equal to 0.061 V squared. So that is this resistance, friction, is going to be equal to, what was that, 0.61. And he's got a V squared, so it's proportional, this resistive force. He's not calling it R like we did over here, where R was proportional to the velocity. This is proportional to the square of the velocity. And so we've got this race car. Now, when he's taking off here, he's driving through here. He's got, he's traveling. He's got and he's just going to cross the finish line here. So he actually, we're going to start the problem at the finish line, because he's going to be coming across here. He's crossing the finish line. It's 175 miles per hour. That turns out to be, I have the conversion there, to 78.2 meters per second squared. Oh, I want to be in SI units. This thing here he says that the air friction is 0.061 v squared, where v is measured in meters per second and F is measured in newtons. That takes care of our units. So we need to be in meters per second and newtons. Okay, and he wants to know how much time would it take for the car to slow down to 60 miles per hour. So the idea is, again, he's coming across the finish line, he switches into neutral, and this is where we actually start the problem at the finish line. This is going to have this resistive force that's going to be slowing him down. That resistive force, or just F, is again 0.61 times v squared. And that's the only force that's acting in let's say, the x direction. Okay, now we're going to follow something very similar to this idea here, although the math is going to be a lot simpler. I'm going to say, okay, the sum of the forces have to equal ma. The sum of the forces, and I'm going to do this in the x direction, is we get a negative force. So I get a negative 0.61 v squared is equal to m a, and a should be equal to dv dt. So again, I've got a differential equation. And the spirit is the same way. Once I get this thing set up, I want to get v as a function of time, but I got a v here, and I've got, inside the derivative. So what I need to do is separate variables, similar to what I did over there, although not nearly as bad. I'm going to bring the dt up here. Maybe I'll keep the 0.0161 times dt. And then for over here, I'm going to have an m dv, and I'm going to bring the v squared here. I like doing this as v to the minus 2 dv. And then I can integrate both sides. So if I integrate this, and I'll pull out, let's say, the minus 0.61, I'm going to be integrating dt. I'm going to have some limits. I'm going to go from 0 to some time t. And I want that to be equal to, I'm going to integrate this. This is going to be the mass. And then I'm going to go, I want to integrate and I want to add, so this is going to be v to the minus 1. Wait a minute, let me not do that just yet. Let me do this as an integral here before I get ahead of myself. V to the minus 2 dv. Need a break here. Okay, and at t equal to 0, the v is it 0? No, it was 175 miles per hour, or 78.2 meters per second. And we want to get the time when it's going what? So, yeah, he's going to slow down is when v final is going to be 60 miles per hour. Oh, I did a conversion on that too. That was, in terms of meters per second, would be 26.8 meters per second. So I want to go to 26.8 meters per second. The limits can definitely help us in this case. Then when I integrate this, let me pull the mass out. I've got the velocity squared. This now becomes, integrating this becomes, I add 1, so that's going to be v to the minus 1, evaluated at 78.2 to 26.8. Let's see, I forgot a minus sign here. Okay, so I think that minus sign will cancel for over here, so I end up with 0.61 t is going to be equal to, I'm going to have, again, these minus signs are going to cancel through here, and that's going to be mass, and then I'm going to have a 1 over 26.8 minus 1 over 78.2. Anyway, you can do the math. It gives us the mass of the car, 1,000 kilograms. And you can solve for the time. and I solve for it. I got 40.2 seconds. So he's done this problem a number of different times, number of different ways. Sometimes he has a pitcher throwing a fastball, and he's going to be throwing it from the mound at some speed. And he wants to know what speed it's going to be crossing, like, home plate. Question?
How did the negatives cancel out?
I apologize. I get kind of sloppy here. This was negative. This was negative, and okay, maybe I shouldn't have. I got getting too slick there. There should have been a negative there. This was still positive. This one was negative. And so I went in, I kind of trying to do it quick and slightly, and so I got rid of these guys, but then I had to change that to negative. Well, we'll just leave this here like this, and then we'll make those minus signs, let's say, go away here. So would be the best. Okay. All right, a little bit tricky. Okay, I kind of taking you brutally through this math. This is definitely a hard one. We did kind of do the same thing where we are still playing with F equals ma. We go ahead and put these things in here, but we end up with this differential equation. We got to solve for v, and I've got it locked up both here algebraically as well as in a derivative. So we have to do this separation of variables. So take a close look at these moves, and then realize you need to do the integration. And depending on the problem, this is kind of how it progresses. And the math of this is not nearly as nasty as that math. Okay, that kind of wraps up chapter 6. Yes?
What about the C after you take the interval?
Okay, I did a definite integral here. Yeah, I didn't do it over here, kind of just mainly wanted to talk about that C a bit. I could have gotten around it. That is an advantage to doing limits of integration. They can very often really help your work. You made use of them over here. And if you do limits of integration, you don't need to deal with that integration constant. And so that can actually be very nice when you get confident enough in your calculus that you trust it. Okay, what we'll do is we're going to come back. Let's take a break for about 10-15 minutes. We'll come back, and while we've got some energy, we'll probably go maybe till 4, maybe 4:20, 4:30 at the longest. I hope that works with people. So let's take a break from now. The energy methods that are coming up, I think you're going to find that once you catch on to them, they're relatively easy. If you haven't gotten into energy methods, this would be a good time to get into energy methods, because it's going to be costly if you don't know about them.